So today we're going to start our unit on liquids and solids, and we're going to talk about the first two sections of this unit, intermolecular forces, and then properties of liquids, and then the rest of the chapter is kind of about solids. Okay, so section 1 is intermolecular forces. Now there is a difference between intra and inter. Okay, intramolecular forces means it's within the molecule. So if you remember when we talked about like polarity and the dipoles, we were talking about a dipole within a bond between two atoms in a molecule. And what we're going to focus on, okay, so this involves sharing electrons. What we're going to focus on is intermolecular forces. This is between molecules. So if you think about, one molecule of water, if we have a glass of water, it's a ton of molecules all bonded together. And so we're going to look at the forces between molecules. These are involved in change of state, okay, going from solid to liquid to gas. You have to break the bonds between those molecules. And these are weaker than either covalent or ionic bonding. So those are intramolecular forces. So let's look at some different types. The first type is a dipole-dipole force. Okay, this acts between polar molecules. So the reason it's called a dipole-dipole is because in order to have a polar molecule, you have to have a dipole in that bond. And so that's why we're calling it dipole-dipole, because it's between two polar molecules. So the molecules will orient themselves with each other to maximize the positive-negative attraction and minimize the either positive to positive or negative to negative, basically repulsion. So the strength of these forces will decrease as the distance between the dipoles increases. Okay, so let's look at HCl, for example. So here we have a covalent bond, okay, but that is an intramolecular bond. Okay, here is our intermolecular attraction. Because we have polar bonds on each of the H to Cl's, these are polar molecules, and so the bond between those two molecules is going to be that intermolecular dipole-dipole bond. Okay, if we look at some HCl's, we know that there is a dipole towards the chlorine, and so we would consider these to be polar molecules, and so the bond between each of those polar molecules is our intermolecular force, and in this case, because it is between two polar molecules, it's a dipole-dipole. Okay, the next one is hydrogen bonding. Now this is a little bit easier to identify, although polar molecules, we should be comfortable with identifying those. This is a very strong type of dipole-dipole bond, so it's kind of a subset of the dipole-dipole. This is due to the fact that there is a large bond polarity and a close proximity of the dipoles, because remember we said that as the distance between the dipoles increases, the strength of the bond decreases. But because hydrogen is so small, the proximity of the dipoles is really close, and so it'll create a much stronger bond. So this is considered a very strong bond. Basically, to have a hydrogen bond, you need a hydrogen, and it has to be bound to a very electronegative atom, specifically nitrogen, oxygen, or fluorine. So these are the only three elements in general that you can have bonded to hydrogen to constitute a hydrogen bond. And so the best way to remember this is that hydrogen bonding is fun. Yay! Okay, so let's look. Here's our water molecule. Okay, this is a polar molecule. And so this is a dipole-dipole intermolecular force. Every time we bond one water molecule to the other, we're bonding an oxygen to a hydrogen. And since oxygen is one of our highly electronegative atoms, this creates our hydrogen bond, which is our intermolecular force. Okay, and so all of these pink bonds, this one, and this one, and this one, these are all hydrogen bonds, which are intermolecular forces. Okay, within the molecule, that's our intramolecular, and that's where our dipole is coming from. Okay, hydrogen bonding will also, because it's so strong, and remember we said that these were involved in changes of physical state, hydrogen bonding will influence physical properties such as boiling point. So if we take a look at these three molecules that have much higher boiling points than basically a lot of the others, this is because we have hydrogen bonded to oxygen, which then bonds to a... So let me clarify. It's not the fact that inside the water molecule we have hydrogen to oxygen. It's the fact that when we put more than one hydrogen molecule together, the bonds between those molecules involve oxygen to hydrogen. Same thing with the hydrogen, the hydrofluoric acid, and then the ammonia. So it's not the bond within the molecule, but it's the bond between the molecules that we're looking at here. Okay, so hydrogen bonding also occurs in organic molecules. So organic molecules are those with a carbon chain backbone. So if you take a look at octane, we have several carbons forming this kind of chain. And so instead of writing all the carbons and hydrogens, we just draw this kind of squiggly shape, and each kind of connection of the lines represents a carbon atom. Okay, if we look at a specific type of organic molecule, which is an alcohol, so alcohols are recognized because of their OH, what's called a functional group. And so because we have this OH bonding to other alcohols with OHs, we're going to have hydrogen bonding going on. And so that makes the bond much stronger between the molecules of alcohol, which then increases the boiling point because it takes more energy to break those bonds. Okay, so we talked about how it has the OH functional group, and that involves the hydrogen bonding, which makes the boiling point higher. Okay, so another type of force are London dispersion forces. These are a bit more general, I guess. They exist among noble gas atoms and nonpolar molecules. So we talked about intermolecular forces that exist between polar molecules. London dispersion kind of applies kind of to everything else. Okay, their importance increases as the size of the atom increases. So the bigger the atom, the more of a force London dispersion forces are going to be. Momentary non-symmetrical electron distribution can create a temporary dipole. So if you think about, how the electrons are always moving within the bonds, between bonds, if we all of a sudden have like this non-even electron spread, then we're going to get a temporary dipole, right? Because you have more electrons on one side than the other. And this can lead to interatomic attraction that is weak and short-lived. It's going to be really significant for larger atoms, and so this can also be another cause of London dispersion forces. Noble gases have really low freezing points, and so this means that the atoms must really slow down in order for interactions to be strong enough to get that solid. And that's why. So because it has a low freezing point, those forces have to be really strong in order to get them to bond as a solid, and that's why the freezing point is so low. Okay, nonpolar molecules lack that permanent dipole moment that polar molecules have, and so they will use London dispersion forces to attract each other instead of using, like the hydrogen bonds between the molecules or dipole-dipole bonds between molecules. Okay, so our second section we're going to talk about today is just some properties of liquids. Okay, liquids have a low compressibility, they aren't rigid, and they have a high density. So let's look at some other properties such as surface tension. Okay, well, surface tension is the resistance of a liquid to increase its surface area, and this is due to an uneven pull at the surface due to intermolecular forces. So if you take a look at our bubble, like if you're washing your car, the water is going to form droplets, right? So it's just going to kind of spread all over. And the reason it forms droplets is because of this uneven pull between water molecules at the surface and water molecules, kind of down further into the water bubble. So these ones in the center are exerting forces on all the other water molecules around it, and so it's this even pull. But if you go to the surface, and especially if we look at this picture over here, now they're only getting these 3 forces versus this one that's getting an even pull all around. And so because it doesn't have any force up top, it's uneven, and so it's pulling it really tight horizontally, which is creating that surface area. Think about like a trampoline if it gets pulled really tight. So large intermolecular forces means a high surface tension. So because water has those hydrogen bonds between the water molecules, that's going to create really high surface tension. If you've ever tried a beaker of water and then putting like a paper clip on the top of that beaker of water, it should sit on the top because of that high surface tension and those high or large intermolecular forces. Okay, another property of liquids is capillary action, and this is rising of a liquid in a narrow tube, and it's basically a balance or imbalance of two types of forces. The first type is a cohesive force. So this involves intermolecular forces among the molecules of the liquid. So whether it's water or in this case it's mercury or whatever, the cohesive force is the intermolecular forces of that liquid. The other force at play here is the adhesive force, and this is between the liquid and the container. So whether the container be like a glass beaker, a plastic container, whatever you're holding your liquid in. In order to form a meniscus and get that liquid to kind of rise up the side of the tube, the adhesive force, the force between the liquid and the container, needs to be greater than the cohesive force, which is the force present between the molecules of the liquid. And that's where we get what's called the meniscus. So in a lab, if you're ever reading the meniscus, you'll always read the lowest part of the curve, and that's your meniscus. Now take a look at mercury. Mercury has almost the opposite, right? So it's curved the other direction, which probably means that the cohesive force is stronger than the adhesive force. Okay, another property of a liquid is viscosity, and this is a liquid's resistance to flow. So again, it's due to large intermolecular forces. So the larger the intermolecular force, the higher the viscosity. The less likely it is to flow, or the more resistance it has to flow. And this is also based on molecular complexity. So if we have this really like bulky molecule, like a bigger molecule of sugar versus like C6H12O6 versus like, I don't know, a smaller sugar molecule, those large molecules are going to all tangle up, and so it makes them harder to pour. Okay, and so if we look at the difference between water, light syrup, and heavy syrup, the heavy syrup has the highest viscosity, which means it's going to have probably larger intermolecular forces and or bigger molecular complexity. Okay, so it's really difficult to make a structural model for liquids. The strong intermolecular forces and other significant molecular motions are what's in play here for a liquid. So unlike gases with negligible intermolecular forces, and then solids which have really strong intermolecular forces, they're kind of in the middle. So it's kind of difficult to model them all the time.